All right, welcome to this explainer. Today, we're tackling the literal engine powering the apps you use every single day. We are talking about machine learning. Now, our goal today is to demystify this entirely. We're going to bypass all the heavy, intimidating equations and focus purely on the logic, exploring exactly how these systems actually learn by using clear, everyday examples. Let's dive in. So here's our roadmap. We'll start with the big machine learning shift, then move into supervised learning, semi-supervised learning, unsupervised learning, and finally, reinforcement learning.
First up, Section 1, the machine learning shift. We're looking at a totally new paradigm here.
You see, the core formula of computing is fundamentally changing. In traditional programming, a human programmer writes out explicit instructions. You give the computer the input data, you give it the rules, like, if a student scores 90 or above, give them an A, and the computer uses those specific rules to produce an output. But machine learning, it flips this entirely on its head. With ML, you give the computer the input data along with the correct answers, and the algorithm itself figures out what the rules actually are. It discovers the hidden patterns automatically, so it can make predictions on brand new data later on. It's a real game changer.
Think about traditional programming like a chef who can only blindly follow a recipe. They've got the ingredients and the step-by-step instructions. Now they'll bake a perfect cake as long as the recipe is perfect, but they can't invent a new dish. Machine learning, on the other hand, is like a chef learning to cook by tasting thousands of different dishes. The chef notices the ingredients, the textures, the sweet or spicy flavor patterns, and over time they learn the underlying rules of cooking. They can eventually create entirely new recipes without ever being explicitly instructed. Basically, traditional programming tells the computer how to solve a problem, while machine learning allows it to learn how.
Let's look at why this shift is absolutely crucial. If you wanted to teach a computer to identify cats and dogs using traditional programming, you'd have to write out rules like, if the ears are pointed and whiskers are visible, it's a cat. If the snout is long, it's a dog. But in reality, there are just way too many variations. Those rigid rules will inevitably fail. But with the machine learning approach, you just provide thousands of labeled images of cats and dogs. The computer looks at the ear shapes, the eye patterns, the fur textures, and it learns those complex patterns all on its own. It can then look at a brand new, unseen image and accurately predict if it's looking at a golden retriever or a tabby cat.
Okay, moving on to Section 2. Let's talk about supervised learning, which is essentially guided training. So the absolutely critical point to understand here is that supervised learning relies entirely on labeled data. This is the linchpin of the whole operation. You can think of labeled data as the definitive answer key. You aren't just handing the computer random data. You're giving it the data along with the exact correct output you want it to predict. The model then studies this paired information to learn the relationship between the inputs and the outputs.
To make this super concrete, imagine a teacher guiding a student. The teacher holds up a flashcard of an apple and literally says, "This is an apple," then a banana, then an orange. That is our labeled training data. The student's brain starts forming patterns, like, okay, apples are red and round with a little stem. Once the student has learned the patterns, the teacher holds up a new, unseen picture of an apple and asks, "What is this?" Because of that guided, supervised training, the student can accurately predict the correct label. A machine learning model works exactly the same way.
Now, supervised learning basically has two main jobs it can do for us, depending on what kind of answer we're looking for. The first is classification. This is when the model predicts specific categories. For example, sorting your emails into spam or not spam, predicting if a student will pass or fail, or distinguishing between a cat and a dog. The second job is regression. Instead of sorting things into buckets, regression predicts continuous numerical values. Think about forecasting things like house prices, estimating tomorrow's temperature, or projecting salary trends.
Here's a fantastic real-world example of regression in action. Say we want to predict the price of a house. We feed the model historical data, maybe houses of 800 square feet sold for $120,000, houses of 1,500 square feet sold for $225,000, and so on. The model learns the continuous mathematical relationship. As the size increases, the price increases. So when a brand new, unseen house hits the market that is, say, 1,600 square feet, our trained model can accurately predict that it should be priced around $240,000. It learned from the past to predict an exact number for the future.
All right, Section 3, semi-supervised learning, where we use partial labels.
The harsh reality is, labeling data manually is incredibly expensive and it takes forever. Semi-supervised learning is a brilliantly resourceful workaround for that.
Step 1. We start with just a really small amount of data that a human has carefully labeled. Step 2. We throw in a massive mountain of raw, completely unlabeled data. Step 3 is where the magic happens. The model uses that tiny set of answers it does have to help it find hidden relationships and patterns across the vast unlabeled data set. Ultimately, Step 4 gives us a much smarter, more accurate model without the massive manual headache of labeling every single thing.
Imagine you start with just a few explicitly labeled pictures of dogs and cats, but then you also have a huge, overwhelming sea of unlabeled animal photos. The algorithm learns the basic features of a dog from the few labeled examples, and then it applies that knowledge to sort through and learn from the massive unlabeled pile. The system basically teaches itself to generalize, growing so much smarter than if it had only studied the small labeled dataset alone.
So, why does this matter in the real world? Well, think about really crucial fields like medical diagnostics. Imagine a hospital has 50,000 medical x-rays. Expert doctors simply do not have the time to sit down and manually label every single one of those 50,000 images as healthy or sick. Expert time is way too scarce. But by using semi-supervised learning, doctors only need to label a tiny fraction of those x-rays. The model can then leverage that foundational knowledge to learn from the rest of the 50,000 unlabeled scans. It's literally accelerating medical research and diagnosis tools.
That brings us to Section 4, unsupervised learning, or finding patterns.
Now, in unsupervised learning, the training wheels are completely off. There is absolutely zero labeled data. No correct answers are provided. You are handing the algorithm pure chaos and asking it to find the structure. Imagine you're dropped into a massive library where none of the books have titles, genres, or spine labels. No one tells you the categories. You have to start grouping the books yourself. Maybe you notice some are grouped by size, others by language, or perhaps by similar cover art. You're discovering the categories entirely on your own. And that is exactly what an unsupervised learning algorithm does with raw data.
You actually interact with unsupervised learning all the time without even realizing it. When a company segments its customers into different marketing groups based on buying habits, that's unsupervised learning. When a social media app recommends a new friend to you, it's finding hidden clusters in your network. A really fun example is association rule mining. This is the algorithm supermarket chains use when they analyze thousands of receipts and suddenly discover that people who buy bread often buy butter. No one ever told the machine they go together. The algorithm just found that hidden relationship buried in the raw purchase data.
Finally, we hit Section 5, reinforcement learning, which is all about earning rewards.
If supervised learning is like a teacher with flashcards, reinforcement learning is basically a gamer playing a video game through pure trial and error. The model, which we call the agent, is dropped into a situation and learns entirely through a system of rewards and penalties. If it takes a good action, it earns points. If it takes a bad action, it loses points. The machine's sole objective is to figure out the best possible sequence of moves to maximize its total reward over time.
To truly grasp this, let's break down the core terminology here. First, we have the agent. This is the learner itself, like a physical robot or the software driving an autonomous car. Next is the environment, the world the agent is operating in, like a physical road or a digital chessboard. Then we have the action, what the agent actually does, like steering left or moving a night piece. And finally, the reward, the feedback loop. Did the car stay in its lane? Reward. Did the robot drop the package? Penalty. By repeating this loop millions of times, the machine learns incredibly complex behaviors.
Which brings us to the end of our explainer. We've seen how computing has just dramatically shifted. Instead of just doing what they're explicitly told, systems can now learn from guided labels, scrape profound meaning from massive unlabeled datasets, discover hidden market patterns, and even teach themselves to navigate the physical world through trial and error. As machines move from blindly following our recipes to tasting the data and writing their own menus, the possibilities are truly limitless. So the only question left for you is, what complex problem will you ask them to solve next? Thanks for joining me on this explainer, and keep learning.